Okay, welcome everyone to the Colloquium. Today we're happy to have Professor Jae-Hoon Kwon, who got his PhD from Seoul National University, and after several jobs, including at the University of Seoul and Sungkyunkwan, is now a professor and chair of the math department at SNU. Professor Kwon will talk about super duality and quantum affine algebras, and let's welcome him to the Colloquium.
Thanks for the introduction and also inviting me to Kwon. I'm really happy to be here again. My last visit to Kwon was, I think, 7 years ago. Okay. So today I will talk about, as introduced, superduality and quantum affine algebra. Quite a technical title, but I'm going to talk about some topics which I have been interested in recent years. But this is a colloquium talk, so I will focus more on the basic background, more than half of my time. Okay, so let me start with the background, representation of Lie algebras. So, okay, the representation theory is, roughly speaking, probably you may know that it's a study of symmetries on a vector space. There's naive meaning. And in a more systematic way, actually, it reduces to a study of an algebra, associative algebra, by linear operators acting on a vector space. So we study the action of an algebra on a certain space, not the structure of the algebra itself. So more rigorously, to study this kind of thing, we define a representation of an algebra as follows. So given an associative algebra A, we consider an algebra homomorphism from A to a more natural associative algebra consisting of a linear endomorphism of a certain vector space. So our algebra realized as a linear operators on various vector spaces. Okay. So the main questions in representation theory is the classification and construction and finding characters of a simple or irreducible A module. So simple means, or irreducible A module means that the vector space V, once it has an action of an A algebra, then we can think of a subspace which is still stable under the action of an algebra. But the simple ones is the one which doesn't have no proper non-trivial subspace stable under the action of an algebra. So the basic question is, what are these simple objects of A module? And then once we have a classification, then how to construct a simple module. And also together with the construction is usually a very difficult problem. So first we may ask, how big is the simple module? Or what's the dimension of a simple module? And this can be asking what's the character of a given thing. I will define more precisely what the character is. And also together with these basic questions, many people are interested in not single object. We consider the collection of all, or the family of A modules satisfying certain conditions. Then we consider the gross and deep groups. And then the question might be, what's the structure of the gross and deep groups? So let me think about more concrete symmetries which are interesting. So a natural group or family of symmetries is an algebraic or Lie group. So we started from a vector space, and then we can consider invertible linear or linear maps, but we collect all the invertible linear maps, then they form a group. So we have a group of we have an action of a general linear group on a given vector space. And to study the action of symmetries, one more algebraic way or a linear algebraic way, an approach is to consider its tangent space of a given algebraic or Lie group, which is called the Lie algebra. And it turns out that the representation theory of Lie algebra has very rich structures, especially when the Lie algebra is a complex simple Lie algebra. So this notion was actually classified by Killing and Cartan very long ago. Also, it has a very nice structure. And when we want to study the representation of semi-simple Lie algebra or simple Lie algebra, then since the Lie algebra is a non-associative algebra, so we want to we may replace the Lie algebra G by an associative algebra, which is called the universal enveloping algebra G. So it is an infinite dimensional associative algebra which contains our Lie algebra as a subspace, and the usual commutator gives the original Lie bracket of a Lie algebra. And the representation of G is exactly the same as the representation of enveloping algebra of G. And the advantage of using enveloping algebra is that now we can apply more general theory of representation of associative algebra. Anyway, when we think of a representation of a simple Lie algebra, then many good properties were proved quite long ago, mainly due to Cartan et al. For example, any finite dimensional representation of simple Lie algebra is semi-simple. That means it decomposes into, or it is a direct sum of simple modules. And also the classification of simple modules was also given. And the dimension is also very explicitly known, which is called the Weil character form. So now we may move on to a more general class of representation of simple Lie algebra. But the category of all UG module is too big to study. So instead, based on some nice properties of finite dimensional representation of simple Lie algebra, the early 70s, Bernstein, Gelfand, and Gelfand introduced a category which has been shown to have a very rich and beautiful structure, which is now called the BGG category. So it is the category of G modules, which has the following properties. So first condition is that it should be finitely generated. And the second condition is that it is a semi-simple H module. So what is H? H is a Cartan subalgebra of our simple Lie algebra, which is a maximal commutative subalgebra. And one good property of Cartan subalgebra is that whenever we have a finite dimensional representation of a simple Lie algebra, the Cartan subalgebra always acts simply. So that means it has eigenspace decomposition with respect to our Cartan subalgebra. So it has eigenspace decomposition as follows. And it should be also locally finite B module, and B is another subalgebra of our simple Lie algebra G, which is there is a typo, it's B, it's a maximal sub of Lie algebra. But the condition is not very complete.
What's an example of G, B, and H?
Oh, okay. So one of the typical examples of simple Lie algebra is a special linear Lie algebra, the subspace of a Gillian with trace 0. And the Cartan is the subalgebra of diagonal matrices, and the Borel is the subalgebra of upper triangle. Okay, so let me briefly recall the irreducible or simple modules over our simple Lie algebra. Then how to obtain, what's the character of this simple module. So we start from one-dimensional module over the Borel subalgebra. So B is solvable. So every simple module is one-dimensional. So we start from some one-dimensional module, but depending on this weight with respect to the action of the Cartan submatrix. Then we consider induced representation to the whole enveloping algebra of G. It is called the Vollmer module. It's a very big. Usually, it's an infinite dimensional space, and the structure is relatively simple. But using this Vollmer module, we can take a maximal quotient. So there is a unique maximal proper Seoul module of this Vollmer module. So we denote the by L of lambda, the maximal subquotient. So it is the irreducible, of course, since it is a maximal quotient, it's an irreducible representation of G. Then these irreducibles are actually all the simple module or irreducible modules in our BGG category. So the classification of simple object in the BGG category is relatively easy. So the next question is, what's the character? Actually, I didn't give a definition of a character. So roughly speaking, it is a dimension of the representation. But since it is an infinite dimension, usually in general it is infinite dimensional. So it doesn't make sense to ask what's the dimension of this representation. But our category, the second condition of the object in this category, so it should be semi-simple with respect to the action of the Cartan subalgebra. So it has eigenspace decomposition, and each space is finite dimensional. So we consider a generating function of the dimension of each weight space. So that's the character. Okay, so let me introduce what's the character of each simple module, irreducible module. The first one important property is that our Vollmer module has a finite composition series. That means it has only finitely many simple simple objects inside. So when it considers, so its character of the character of a Vollmer module is a finite linear combination of the character of the irreducible representation, and also the coefficient of the character of irreducible module in the character of Vollmer module is actually the composition multiplicity of each simples in this Vollmer module. And then what is good here is that the highest weights mu here appearing in this expression is that with respect to a certain partial order, the mu here is always less than or equal to our highest weight lambda. So that means that if we consider the family of characters of Vollmer module and the character of simple modules, then they might be a kind of basis of a certain group. Then this composition multiplicity actually gives the transition matrix between two bases, and this triangularity means that our transition matrix is a unit upper triangle. So in principle, we can compute its inverse. So that means once we have a decomposition multiplicity, then in principle, we can compute this inverse matrices so that the character of a simple can be given as a linear combination of a character of a Vollmer. And the reason why we consider the transition matrix between simple and Vollmer is that the character of Vollmer is very simple. So once we know the decomposition numbers, and since the character of Vollmer is very simple, so then we obtain the character formula of the simple module. So there is the conjecture of the simple modules, which is called the Kazan-Lustig conjecture, and also proved by the Brzezinski, Kashiwara, and Velis-Feinstein quite long ago. So it is given by the following somehow complicated looking formula. I'm not going to explain all the details of this formula, but roughly speaking, the result is that the character of Vollmer is given the decomposition number of the simple object in this former is given by specializing a certain polynomial at q equals 1. And also, the inverse formula is also given by specializing this kind of polynomial when at q equals 1. And the polynomial p here is actually have two parameters coming from the Lie group of simple Lie algebra. So Lie group is the finite group which plays a very important role when you understand the structure of a simple Lie algebra. So it's a combinatorial information from the structure of the simple Lie algebra. So the Kazan-Lustig formula is as follows. So the decomposition multiplicity can be obtained by specializing a nice family of polynomial. Then I did, but I haven't defined this polynomial. In the next slide. So the Kazan-Lustig polynomials are also coming from kind of a transition matrix between two special bases of a Hecke algebra associated to our Lie group W. Then what is a Hecke algebra? The Hecke algebra is the Q deformation of the group algebra of our Lie group. So here there are two bases of our Hecke algebra of this Lie group. One is CW parameterized by the Lie group element, and the other one is a TX, also parameterized by Lie group element. The TX is the more standard one. So it is just a product of the very elementary generator of our Hecke algebra. Then there is some non-trivial non-trivial symmetry on the Hecke algebra, and then the canonical basis is defined as a basis of our Hecke algebra, which is invariant on the symmetry and also satisfying certain triangularity property.
What is Q?
Q is just a formal variable. So the CW is just an algebra over the complex number. The Hecke algebra is an algebra of the ring of rational function with the formal variable. So you see that there is a key point here. Okay, what I want to say is that the decomposition multiplies are obtained from a transition matrix, sometimes specialized, between some standard basis and some non-trivial but good basis of an algebra. Probably, maybe you may have seen this kind of phenomena or a result in a more elementary picture when you study the representation of finite groups, especially when you want to find the irreducible characters of a finite dimensional irreducible representation of a symmetric group over a field of characteristic 0, then actually that irreducible character can be computed by transition matrices between some good basis of a ring of symmetric function. That's the classical result of a problem. But somehow this phenomenon is very similar to the Kazan-Lustig conjecture. Okay, let me move on to another object, which is a little more closer to the title of this talk. So that's the superalgebra. So since I have talked about the simple Lie algebra, which has very nice representation theory, and in the late 70s, a kind of variation or a generalization of Lie algebra has been introduced. Which comes naturally from theoretical physics, sometimes called supersymmetry, but I'm not the expert from physics, so I just briefly explain what's supersymmetry. So it is a symmetry is acting on a space now having some kind of zeta grade. Or in terms of more physical object, it is related to a vector space which is generated by mixed by fermion and boson. So roughly speaking, fermions you may imagine a kind of very big space generated by the commuting variables, and also anti-commuting variable. So when you consider only the space generated by the commuting variables, you may think of it as a polynomial algebra. But we also consider inside this space also another family of variables which are anti-commuting. So we consider a mixed space. We consider space mixed with the commuting and anti-commuting, and physically this also corresponds to fermion bosons. Then we consider the grading on this space. We grade so the zeta grading. So we the commuting variables we define the degree of this commuting variable to be 0, and we define the grading of the anti-commuting variable to be 1 or up. Then each monomial has a zeta grading, and the whole space, the polynomial algebra, has a zeta grading. And then we consider symmetry acting on this space. And since the space has a zeta grading, our linear operator also may be naturally endowed with the zeta grading. So the even linear morphism is the linear map preserving the grading, and the odd linear operator is the linear operator which shifts the grade by 1. That's the supersymmetry. So more rigorously, based on this the notion, we can think of a super analog or zeta-graded analog of Lie algebra, which is called the Lie superalgebra. So it is a zeta-graded space with the super bracket. It satisfies the super analog of our usual definition of the Lie algebra. So first condition is super skew symmetry. So here the plus minus happens depending on the parity of our homogeneous vector. The P of X, the parity, and the super is equivalent. So let me give an easy example. So let V be a finite dimensional vector space with a zeta grading. So let me just call it a super space. So V0 is the even subspace or space with degree 0, and V1 is the subspace of degree 1. Then we consider the space of linear endomorphism of this superspace. As I mentioned just briefly in the last slide, from the zeta grading of our space V, we can define the grading, zeta grading on our linear endomorphism. Epsilon is 0 or 1. So the even one is the linear map which preserves the grading, and odd one is the shift by. Then this space with the zeta grading. So now our space of linear endomorphism becomes the zeta grading as well. And it has a structure of this superalgebra where the super bracket is given by the super commutator. So for the homogeneous elements, we define, so we twist the commutator depending on the parity of our elements. So that's anyway, so this typical example of the superalgebra is called the general linear Lie superalgebra. So when the other space is trivial, then it is just a general linear Lie algebra, which you may be more familiar with. And also there is an analog for the orthogonal or symplectic version of Lie superalgebra, which is called orthosymplectic. So probably you know that the special orthogonal Lie algebra is the subalgebra of SLN, which preserves symmetric bilinear form on our space, vector space V, which SLN acts in a natural way. And also there is a version of a symplectic version when n is even, which is the subalgebra, which preserves the skew-symmetric bilinear form on our vector space. So there is a superanalogue, which is called OSP. So this is a subalgebra preserving a supersymmetric bilinear form on our superspace. So for later use, I will use this notation. So when the space is when the superspace has the superdimension m/n, so the even part is m and odd part is dimension n, then let me just denote it by GLMN. And OSPMN is the subalgebra of this GL. So I'm going to talk about
What is supersymmetric bilinear form? What is the definition?
so it is symmetric on when it is restricted on even space. It is skew symmetric when it is restricted on odd space. So now let me introduce briefly review what is known about the finite dimensional irreducible representation. Its classification is the irreducible character. Okay, so the first classification of simple Lie superalgebra has been done by Cass in all these late 70s, when actually he systematically developed introduced and developed the theory of the simple Lie superalgebra. Then after the classification, people became more interested in the representation theory of simple Lie superalgebra. But people found that the representation theory of simple Lie superalgebra G is not parallel to that of a simple Lie algebra and more. There is some crucial difference between them. And then a couple of major difference or major obstacle which causes the crucial difference between two representation theories that finite dimensional G module is not always semi-simple in general. And also the more fundamental difference is that the Borel subalgebra of a simple Lie superalgebras are not conjugate in general. So it became more non-trivial and challenging problem to find the irreducible character of a simple Lie superalgebra. And that problem and of course the related causality theory have been studied intensively for the last couple of decades. So let me briefly review the known results about the irreducible character problem. So let G be a simple Lie superalgebra. Then all finite be the category of finite dimensional G module with the simple parameterized by certain explicit set of highest weights, which I'm not going to describe in detail. Right. Yes, as I mentioned, the category O, even for finite dimensional representation, and character L lambda become more non-trivial compared to semi-simple Lie algebra. So there have been several independent approaches to compute the character of L lambda, and each of them has its own advantages, providing a different insight into this category. So let me introduce what are the major approaches to this problem. Okay, so the first one is the closer to the classical approach to the causality conjecture in terms of geometry of flag variety. So there is a super version of flag variety introduced by Urimani. And for GLMN, it was given by Seganova. And for PLD super, it's another class of simple Lie superalgebra, which I'm not going to define here. But anyway, QN done by Pankov, Seganova, and OSP case was also done by those two. And another approach, which is I'm more interested in, more surprising, is that it's the solution given by the theory of a canonical basis of quantum groups. So, for the GLMN and Q of n for integrable with integral weight, it was done by Brundan, and also Qn partially with the half integral weight by Chang and myself. And the approach here is that, so we consider the category of the growth and degrowth of this category, and the approach is that we realize this growth and degrowth as a certain very explicit representation of a quantum group of some classical types, GL type A, B infinity type B, and C infinity, and so-called the Fock space. And then, so we consider some very explicit representation of a quantum group. Then we apply the theory of a canonical basis. Then what is canonical basis? I don't have enough time to explain the details of this one. But anyway, there is a very non-trivial, very highly non-trivial, but having very good property, some basis of a representation of quantum group, which is defined, basically defined in terms of R matrix coming from the quantum group. Then the Brundan proved that the canonical basis, and it corresponds to, so this Fock space is isomorphic to the growth and degrowth of this category, and when Q is specialized to 1, and then he showed that the canonical basis here corresponds to projective object, and also dual canonical basis corresponds to irreducible object, and standard base corresponds to some standard object here. And then on the left-hand side, the dual canonical basis can be, in this case, can be explicitly computed. So once we establish this corresponds, and then we can compute the irreducible character of the Lie superalgebra. So this connection was very remarkable discovery in the representation of the Lie superalgebra. And it is also somehow related to the picture of the Kazanostic theory, which I have introduced in the Bijouji category. So the character problem of an irreducible character problem in Bijouji category was given by considering considering a transition matrix between two nice bases of the isomorphism class of a given category, and the transition matrix was obtained by the Kazanostic polynomial, which is appearing as a transition matrix between the two non-standard bases of Hecke algebra. So here you can see that so we have some vector space with the action of quantum group, and then we have a very non-trivial basis, canonical basis, and also some very standard basis. So the standard basis means that it is the wedge to deform the exterior algebra. So there is a very explicit. There is the standard basis consisting of wedge product. So the Brundan computed the transition matrix between the canonical basis and the standard wedge basis very explicitly. That gives the character formula of the simple object on the right hand side. So in that sense, it is very similar to the picture of the original Kazanostic conjecture.
Is it possible to view Lie superalgebra in a sense of algebraic groups over C?
There is a counterpart of algebraic super version of algebraic group. That's actually the Seganova's approach was using the supergroup geometry language.
Sorry, is B infinity like the simple Lie algebra of type B?
Yes, it's the thinking diagram. With
Okay. And so B infinity is related to Qn with integral weights and C infinity with half integral weights. Is that the connection?
Yeah. And there is another approach which is called a super duality, and also it was introduced in the title of my talk. It is also a very different approach. And anyway, using this theory, the character of GL element was, and also OSBM 2n, and even it was generalized to the Casimir superalgebra. Then what is a super duality? Let me explain very roughly. So superduality explains conceptually the connection between two the categories of Lie algebra and Lie superalgebra. So on one side, so for example, when we consider GL m/n, then we have not BGG as slightly smaller parabolic BGT category, but still it contains the finite dimensional representation. So we consider parabolic BGT category, and then we consider infinite rank version. And also we consider GM plus n. There is a GLM plus n, then there is a parabolic BGT category, and there is a infinite rank version. And then superduality is the equivalence between these two categories. And this equivalence actually shows that the decomposition multiplicities on the super side is actually given by the Kazan-Lustig polynomial as well. But the parameter of the Kazan-Lustig polynomial given by the Y group element, there is some twist. And the twist is actually described very explicitly. So this theory explains how conceptually the theory of the representation of Lie algebra and Lie superalgebras are related. Then why the theory of representation of Lie superalgebra, even the finite dimensional representation becomes more complicated. So that's the three major approaches to the irreducible character problem for the simple Lie superalgebra. Okay, so now I have continued. So now let me move on to the third object, quantum affine algebra. So now let me briefly review the theory of the finite dimensional representation of the quantum affine algebra, which also has a very rich structure. And how, okay, so let us consider the G hat, the untwisted affine Casimir algebra. That's the infinite dimensional Lie algebra. It is a central extension of this Laurent polynomial extension of a simple Lie algebra. So their finite dimensional representation has been studied by many people for more recently. And actually, the people study the representation theory of this quantum group version, which is called the quantum affine algebra. So here, this is the Drinfeld-Gingras version of quantum group. And the reason why one of the advantage of using quantum group is that compared to the usual Lie algebra, the representation theory of quantum group reveals more information than that of the usual Lie algebra by the theory of canonical basis and the global crystal basis. So let me review the finite dimensional irreducible character problem for the quantum affine algebra. So we consider the finite dimensional UQGM module with at least which is semi-simple with respect to the Cartan part of our quantum group. Then, unlike the case of simple Lie algebra, the affine version, the finite dimensional representative affine Lie algebra or its quantum group is non-semi-simple. It is closed on the tensor, so it is a non-semi-simple tensor category. And the irreducible objects in this category are classified due to Charian principle. And one of the main problems of this representation is to find the character of any irreducible object. It is still open. Only, still in general for any. So here the G hat is untwisted affine Lie algebra, but there is a twisted affine Lie algebra and it's quantum affine algebra. So the irreducible character of the general quantum affine algebra is still open. But anyway, I will talk about how to construct a simple object here and why it is also interesting. So this category is shown to have a very structure. So first, it has a Q analog of character theory, which is called the Q character, introduced by the Frank University. And also, there is a casuistic theory, not for all quantum affine algebra, but for only the simply laced AD type due to Nakajima. And more recently, it was shown that it was observed and conjectured that the cross-ending ring of this category has a cluster algebra structure given by observed by Hernandez and Leclerc. And more recently, this cluster algebra structure is actually can be categorized in the language of representation of quantum affine algebra, which is called the monoidal categorization, which was done by Kashiwara Kim or Park in the last year. So this structure is always very closely related to the irreducible characters. And fundamentally, the structure of this category is related to the R matrix, which is associated to the given quantum group. And the R matrix, roughly speaking, is an operator acting on a tensor product of the objects in this category, intertwining the action of the quantum affine algebra, and also satisfying certain equation called the Yang-Baxter equation. Okay, so let me briefly introduce how the simple module is constructed using in terms of R matrix. So as I mentioned, the structure of this finite dimensional representation category is deeply related to the R matrix. And one can see this feature, for example, when you construct a simple module. So let pi I be the fundamental weight for our base simple Lie algebra G. Then we consider this fundamental representation. And actually, we are considering the action of affine Lie algebra. So there is an extra generator. So associated to that generator, we can consider the spectral parameter. So there is a kind of fundamental object of the the finite dimensional representation of quantum affine algebra, then it is shown that every irreducible object in f of g hat is given by a subquotient of the tensor product of this fundamental representation for some sequence of the fundamental weights and spectral parameters. It should be carefully chosen. Then now we apply the R matrix to the tensor product of two fundamental representation. So usually the R matrix is not the universal R matrix acting on the tensor product of any two fundamental representation. It's not well defined in general. So we first started from the fundamental representation where the spectral parameters are formal variable. When you apply the universal I matrix here, then the image usually lies in this more bigger space where the base scalar is extended to field of rational function in two variables under certain normalization condition. So here the R matrix, it depends on the ratio of these two spectral parameters. So, and it is given by a rational function in this variable. So under the careful specialization of this variable, then we have a well-defined K-linear map on the tensor product of these two fundamental representation to the same one where the tensor order is flipped. So to have a well-defined map, we know the pole of this, the normalized R matrix. And actually the information of pole of the normalized R matrix, the crucial information. So anyway, so there is the important theorem due to Kashiwara to construct the irreducible representation of the UQG hat. So when our the family of fundamental representation, where once they are given and the spectral parameters are chosen such that whenever we have a ratio, Ij is an arbitrary pair, I is smaller than j. For any pair of I and j, our condition is that the ratio of this spectral parameter is not the pole of our normalized I matrix. Then the image of this map, I will explain later, where the tensor product is of the fundamental representation to the same one where the target is the tensor order is in a reverse way. Then the image of this map is irreducible. That's the theory. Then what is the RW0 here? So the RW0 is the composition of our normalized R matrix for any pair of the fundamental representation, where so it acts on the okay. So our R matrix satisfies the Braid relation. So because it's a solution of the Yang-Baxter equation. So the W0 is the longest element in our symmetric group. So for any given reduced expression, our longest element, we can associate composition of so each simple two cycle or the generator of the symmetric group corresponds to the normalized R matrix acting on the neighboring two tensor component. So given a reduced expression of the longest element, we can define this linear map by composing the corresponding R matrix. So once our spectral parameters is satisfying this condition, then we can construct the simple module of a quantum affine algebra. And it looks like the construction is a very, very special gives only some special class of simple modules, but actually it is not. So any irreducible modules can be obtained in this way.
So can you remind me what GS is? GSS is? Longest
This one,
Yes.
symmetric group of S letters. Symmetric group, permutation group.
Okay. So file group you mean?
Sorry.
Is it file group? File group or affine file group?
Not the Lie group. Yeah, it can be viewed as a Lie group of a type A Lie algebra, but it is not related to the type of the quantum affine algebra. So it just so S is the number of tensor vector. So we consider the permutation of the tensor. So that this W0 is the permutation which sends 1 to S to 1. So the longest one can be the symmetric group is generated by the transposition like this. So let me say it is small si. Then longest one can be written as a composition of those generators. Right? Then we associate to each, let me call it a simple reflection. Then we, so if this is the reflection I plus I and I plus 1, then we consider the normalized R matrix acting on the I and I plus first position. That's the R W0. So we consider normalized R matrix acting on the I and I plus 1, and so on.
And these tensor products will generically be reducible, and they will be only be reducible. Is it true they're only reducible for special values of xi?
Just
So you're saying the image of RW naught is an irreducible. Does it happen that most of the time the image is everything on the right hand side, the full tensor product? Or in other words, that RW naught is an isomorphism?
yeah, yeah. So, so generically, RW0 is the isomorphism. In many cases, the tensor product itself is irreducible.
Okay.
And your question is,
If that's the case, if that's true. So it is true that in many cases it will just be reduced. Okay. I think that was my question.
okay, so to know the whole information of normalized I matrix is very important, but usually it is not very difficult. It is very difficult to find the whole of the normalized I matrix. But in case of type A, it's compared to very explicitly. So in case of type A, when we consider the tensor product to fundamental representation, then it is semi-simple with respect to the finite type subalgebra of quantum group. So in case of type A, this is a direct sum of the irreducible representation of UQSLN. Then we can write our normalized R matrix as a linear combination of the projection onto each simple component. Then the coefficient of each projection is given by the following formula. So the pole of this normalized R matrix is given by the zero of the numerator in this coefficient. So now let me talk about, so now I have 5 minutes. So now I will talk about the actually related to the title of this talk. So what I have been recently interested in was the affine analog of the superduality and also the super analog of the quantum affine algebra, representation theory of quantum affine algebra. So let G be a simple Lie superalgebra, and then we can consider an affine analog, affine version, or affine superalgebra associated to G. Then compared to quantum affine algebra or affine Lie algebra, the representative theory of affine Lie superalgebra is very little known so far. So it is natural to ask whether there is a superduality for the quantum affine algebra or it's a quantum version. That was my motivation. And recently, we have shown several evidences for the existence of the affine superduality in case of type A with the polynomial weights and also OSP version. And we constructed a kind of the functor, sometimes equivalence, by constructing a Q analog the truncation functor, which has appeared in the superduality picture, which preserves the normalized R matrix in the theory of the quantum affine algebra, together with this Paul information. So let me briefly explain what are the results in case of type A. So what I have done is constructing a functor explains which connects the finite dimensional representation of quantum affine algebra of type A and the finite dimensional representation of quantum affine superalgebra of type A. So we start with a general linear Lie superalgebra, which parameterized by a sequence of 0, 1. That technically corresponds to the type of Borel of our simple Lie algebra. Then we consider this affine version and its quantum group. And in case of our parameter is homogeneous, that means when epsilon I is all 0, then it's just the usual quantum affine algebra of type A, GL version. And also when epsilon I is all 1, then this is also the quantum affine algebra of type A, but the parameter becomes now in a minus Q inverse. And also when the epsilon is not homogeneous, for example, some of them are 0 and some of them are 1s, then it gives the quantum affine superalgebra associated with GL. Then we consider the finite dimensional polynomial weights, finite dimensional representation with the polynomial weights. Then we constructed some good functors connecting FD epsilon when epsilons are changed. So we consider the alternating parameter sequence of epsilons. And then we have a morphism. We constructed a morphism between the quantum affine superalgebra, GL epsilon hat, and the usual quantum affine algebra of type A, and also the quantum affine superalgebra of standard types. Then this algebra morphism naturally defines a functor between the representations of those quantum affine algebra of finite dimension and with polynomial weight. Then our theorem was that there is truncation functor connecting those three categories. And when the degree is, or when the rank are large enough, then this functor gives equivalence. And the main motivation is that the truncation functor here is basically almost the same as the original superduality functor.
Sorry, what is D? What does D represent?
D is so we consider the representation of polynomial weight.
Of degree D?
Yeah, degree.
Okay.
And also we have constructed an analog for the also symplectic case, so affine superalgebra type D. And then we constructed some exact tensor functors. So we constructed a kind of infinite dimensional representation of the affine OSB, and then we constructed the functors which goes to the finite dimensional representation of usual quantum affine algebra of the type C or D, and also it goes to the kind of infinite dimensional representation, the usual quantum affine algebra of type D or C. So we have some connection between the finite dimensional representations, quantum affine algebra, and some infinite dimensional called oscillator representation of quantum affine algebra, and they are connected by infinite dimensional representation of quantum affine superalgebra, also symplectic type. But we haven't proved yet. We expected it after some kind of taking limit to the infinite rank. It may give an equivalence, but we are expecting that, but we haven't proved it. So anyway, this category O epsilon in the middle is anyway, it's a new category of representation of quantum affine superalgebra, also symplectic. As I mentioned, that we expected these two functors to induce equivalence after suitable infinite rank version. Anyway, there is a BGG category for the quantum affine algebra. So as in the usual superduality case, we expect that the finite dimensional OSB, affine OSB, the category of finite dimensional representation of affine OSB corresponds to a parabolic BGD category of the usual quantum affine algebra. Yeah, that's all.
Any questions or comments? Can you go back to the Taipei equivalences for a second? Yeah, this one.
Yeah.
So here is the motivation to relate FDM plus N with FDM bar N. So if the two TR functors are equivalences, then the two things also become equivalent, right? Was this your main motivation?
Main motivation.
So maybe to me it's slightly unclear what the middle category is, but the left and the right category, to me, they seem more natural, and it seems quite unexpected that they're somewhat like, was it known that they're equivalent before?
Affine case?
Yes.
No.
Okay.
Probably so there is actually there is a hidden equivalence between them. So there is a quantum affine sure duality.
Okay.
And so also this also gives an equivalence between the representation of finite dimensional representation of quantum affine algebra and the representation of Cubic algebra.
Okay.
And actually, we can construct a super analog of the generalized quantum affine sure duality functor.
Okay.
Yeah, so we may actually expect from that point of view that these two categories might be equivalent.
Okay.
By
I see.
Yeah, but what you have done is that there is a direct, somehow these two, these two categories can be actually related to a more bigger representation, more bigger affine Lie parameter.
I see. I see.
And the proof of the equivalence is based on we are using the equivalence of the generalized quantum affine Schrödinger.
Okay. And at this point, do you ever use this R matrices? So you spoke about R matrices before and their poles. Do you use quantum super R matrices? Okay.
We need the fusion construction for the super case as well. So what we have done is that the same, we have a super analog of this Kashima.
You have a super analog of this theorem.
Yeah, there.
And what is, so here VLI is the L exterior, like fundamental weight. What's the equivalent for?
What's the super version of the fundamental
There is a
representation?
super version of the fundamental weight.
Yeah,
Uh-huh.
yeah, there is. We can. So, for example, so now, so we are considering only the polynomial weights.
Okay.
So the fundamental representation has a finite type as a module of the finite type. Actually, it appears in the Schrödinger duality.
Yes.
So their highest weights are parametrized by partitions. So we have a super version of the Schrödinger duality. So we can naturally think of the fundamental representation, which corresponds to the single column Young-Dam.
Okay. Okay. Yeah.
This is just a linguistic question. When you said you have shown several evidences for the superduality, what exactly do you mean? You have shown several evidences for the superduality.
The last theorem is that. So this theorem is that we constructed the exact functor which preserves the tensor product. And so this functor sends the simple to simple. That's important. And also it sends, there is a kind of a standard object here. And this functor sends the standard to standard.
So what I meant was
that actually happens in the superduality picture. So the superduality approach is that the truncation functor preserves the standard and the simple. So to find to have the irreducible character, we actually need the transition matrices between the standard object and irreducible object. So if our functor preserves the standard and irreducible, then actually character problem is solved from the Lie algebra side. So that's the philosophy of superduality. And this functor actually preserves the standard object and simple object. And so this is the category of finite dimensional representation of the usual quantum affine algebra. And there is a Kazanov-Stick theory. So the irreducible characters can be understood as a linear combination of the character of the standard object. And our exact functors are preserved standard and simple. So once we have an equivalence, then so we haven't shown that this is an equivalence yet. But anyway, the irreducible characters actually can be the linear combination of standard object with the same transition matrix here. So that's the.
Can I see the slide where you said so you have shown several evidences for some specific cases?
Oh,
yes. Go back a few.
okay.
Yes. Yeah. So are you saying you proved the existence of superduality, or it's just found some?
So we have proved the equivalence for this case. We have constructed the exact functor only, which preserves standard and simple, but expected to be the equivalence. So superduality is the equivalence between two categories. So we expect that the function we have constructed is
Yeah, I'm just linguistically, why didn't you say we have shown the existence of
we have shown several
not the word evidence?
In this case, it's not evidence. We have proved. Okay. In this case, we have constructed some evidence.
So indication?
Yeah, the superduality means some equivalence. Then we have constructed the exact functor, which we expect to be equivalence. Sorry for confusion.
Any other questions or comments? Can you go back 2 slides forward? Sorry, forward, not backwards. More. No. So again, no. So here you have X, Y is C and D. So you mean the quantum affine algebra of type C and D, so the non-super version.
Yes.
So let's assume you're able to show an equivalence. Was this expected that f of like Cn1 is equivalent to O of Dn1?
Yeah, if they are equivalent, then. But anyway, technically, we have to think of some kind of infinite rank version to have equivalence. But
Okay.
anyway,
And is this infinite rank version known or not? If you disregard, yes, affine, no. I see.
so finite version
Yes,
as a special case of a superduality,
yes.
the integrable representation of the type C
Okay.
corresponds to a kind of oscillator infinite dimensional representation of type D.
So okay.
So this kind of affine version.
Affine
of
version.
the
I understand.
superduality.
Okay. All right. Let's thank the speaker again. There will be snacks in the Hilbert room, and if